Today I am talking about the actual making of a huge model in a new field for myself. I am working on that field from 2009. The first chapter of my presentation is how to start a huge problem. Is an investment. And before making an investment, I am an economist. You have to carefully plan if the return is good. So, first of all, you have to manage with your boss, with your supervisor, with yourself, if it is good to start this kind of heavy, costly in terms of time, work. And my line of activity is that of, first of all, building a tiny proof of concept. In this case, the proof of concept has not been so tiny, because then has been published on Jazz. But if compared with the actual work, this is only a proof of concept. My friends from the Central Bank of Italy, Luca, Claudia, Leandro, and Claudio, wrote a starting model using star logo TNG. Maybe do you know star logo TNG is very close to net logo. Star logo and net logo were very similar in the past. Then star logo has been put in open source. They don't maintain, star logo is from MIT. They don't maintain it anymore, but they started a new version, star logo TNG, the next generation. A little bit open the level. Anyway, what the difference between NetLogo that I like very much in my class, I teach NetLogo. What the difference between NetLogo and StarLogo TNG? This is very close to a video game as a result. So if you look that you have to discuss with your boss has a few time to spend with you to decide if to do the model or not. Think about the Central Bank of Italy. The decision has been taken by one of the central directors, so he has a very, very tight schedule. So you have to demonstrate that it's possible to communicate what do you want to do in a way that is very easy to be understood, the video game. And in my line of work, I have not satisfied with the necessity of programming something like StarLogo requires, because using StarLogo, you are, oh, terrific, sorry for the camera. You are using something like that. You have small cards. Each card is a piece of code. And you are programming, moving around the cards. So when the problem is huge, you have something like this table covered by small cards. It's like a puzzle. And you can have a look to your code moving a window around, you see. So you have to remember, oh, where I've placed the cycle deciding that of those operations. Anyway, if you look at the first glance, it is easy to write the code. You move the, or what I have done, changing this parameter, so like substitute the initial value. But what is interesting here is that you have fall yesterday, maybe will fall also today, but for the payment, from the payment point of view, it seems to be a normal day. But we are running the system at about, I don't know, 3 o'clock in post-meridian. We discover that the liquidity is not sufficient to close the day. So we are expecting that at 8 o'clock, no, at 6 o'clock, some bank will not be able to pay, to close the day. What to do? To put liquidity in the system or not, we have to simulate the part of the day necessary to understand what will arise from the current situation. This is the job we want to do with our simulator. In Europe, we have 2 realistic simulators about payment system among banks. Pay attention, these are payment internal to the bank system. Banks are paying within themselves because clients are ordering to pay, but these are not payment. We have not the firm origin of the payment, we have the effect within the system. We have two realistic models, that of from the Bank of Finland is a wonderful model with about 800 banks within, so absolutely complicated. Also because they trace all the zoo of the rules emerging from the history of different countries. You think we are joining, we are merging economic system, but the rules are very different. So we have to merge also the rule, and they are able to do that. But in their system, they have no unrealistic money market. We are trying to build within our system a realistic money market. It is easy? No. This is the economic system. Do you know this picture? It's coming from the Punch in the 50s, when Professor Phillips, the author of the famous Phillips curve, inflation and employment, tried to build a mechanical model of the economy. And the satirical magazine Punch created this picture, which is very well representing the simplicity of an economic system. Maybe I am, I don't know, this guy, trying to run a model. We are trying to understand and to control a tiny part of a so huge economic, messy, complicated situation. Here you have two links if you want to have a further look to the work. Here you have a page containing a conceptual map of the model, and also this is a line I am following building huge model. To build a conceptual map of the model, first of all for myself, and then for the user and for the other person, guys, working with me. Because quite soon you are lost in a cloud of very complicated parameters, rules, sequences to be followed, and so on. My idea is to put them into the computer, and the conceptual map way simplifies a lot my work. And here you have a link to a formal presentation of the model. It is always a draft, because we are changing continuously it, but the bases are there. So if you want to have a close look to the mathematics behind the model, you can read this paper. And in the future months to ask directly to myself, because we are writing two new papers presenting the same thing in two different ways. This is the conceptual map of the model. I underline the importance of using this tool to explain, first of all, to the creator, the model that we are generating. Oh, sorry, I forgot. The rule of the game, you can interrupt myself anytime you want. I will manage to have some time for the discussion, but if we are lacking of a question, I have a technical appendix to be introduced. Anyway, interrupt me when you want. The core of the model are the banks. And what the banks are agents. Imagine to have about 15,000 payments per day moving around. The payment in the model are envelopes containing all the data of the payment, and they are instrumental agents. Formally are instances of the class of the payments, but are unminded agents. They are absolutely inactive. They do what they have to do. So they go to the bank asking for the payment. The true agents are, in my case, 100 banks. 100 is the number of the active banks in Italy. 800 in the whole Europe. The same bank can be operating in several countries, sure. So 800 is not the sum, is the set of all the banks. What banks are doing? They are receiving the order to do the payment, and they have to decide if to immediate pay, as the rule from the Bank of Italy is asking, or to delay. Delay is risky for the treasurer, but sometimes is necessary. There is a reputation game behind. The idea is, I have to pay. I put in the system the news that I have to pay. If I cannot pay, I wait. Yes, but all the other banks discover that I am not able to pay. So there is a reputation problem behind the decision. Quite complicated. First decision. Second decision, voluntarily I am delaying because I am in Italy. In France they need hot money. I can borrow hot money in France for 5 hours. This is a good deal, not for myself, but for my bank. But what if at the end of the 5 hours the French bank cannot send back the money? I am in an area where I have a huge problem to search for money. The second element is the reproduction of the computerized payment system running in Italy, in France, everywhere in Europe. The RTGS, real-time gross settlement system, is distributed everywhere in Europe. Now the current name is Target 2. The third element is a money market. Here, treasurers are bidding and asking for money, hot money, from now to 4 o'clock in the afternoon, from now to 9 o'clock tomorrow. This is the max in the hot money market, and you pay there an interest rate, an annual interest rate referred to 1 day, so divided by 360, the conventional number of the days in a year, independently from having the money for 1 hour, 10 hours, 24 hours. Is exactly the same. Only the annual rate referred to a day. This is a double auction, continuous double auction market, because you are auctioning to obtain money, so you are offering a price, and you are auctioning to lend money, so you are asking a price. And my Professor Guildford was recalling my model about the stock market. My experience there has facilitated my role in building this kind of market, but a lot of very complicated rules are behind the decision of the banker to borrow or to lend money. So here our agent has a lot of decisions to be done. The first decision is, I have to pay, I delay or I pay immediately. If I delay, I communicate to the system the fact that I cannot pay, or I keep secret my situation, violating the central bank rules. This is quite complicated. The second decision is to lend or to borrow money, also with a reputation problem. And the final decision, the more complicated one, is how to behave to keep the position of the bank in the middle, if possible, of a corridor contained between a min and a max, necessary to be respectful the constraint put from the central bank about the reserve, current money reserve that each bank has to keep in liquidity. This is a simplified explanation, but it is absolutely realistic. Our model is, first of all, reproduced in this simplified scheme. These are all the banks participating in the payment system. You see, I submit a payment. If funds are available, the system settles the payment. If funds are unavailable, the system put my payment in a queue. My funds are virtually kept into the central treasury account in the central bank. This is a virtual situation, but anyway, the central bank knows perfectly what the situation of my accounts is. But what if I decide to do not submit and to delay the payment without submitting? This is one of the origins of a possible domino effect, creating huge crash situation in a day. When we started, I was wrong. We don't start in 2009. We start in 2007, so before the big crash. The unique problem was the delay in payment, and if a huge bank is delaying, all the other banks discover it immediately, and the panic is spreading around the network. But after the crisis in the beginning of 2009, no one was paying in time. All banks were delaying. And no one was participating in the money market. The conventional name is electronic market for interchange deposit, but it is a market for money. No one was participating in the money market because no one was wanted to announce that he had no money, and no one anyway would be borrowing money to other banks. So this was a situation with a monopolistic role of the Bank of Italy, but a very heavy monopolistic role, providing liquidity to all the system. I remember that in the days of January, February, March of 2009, the Bank of Italy was putting each day about 8 billions of euros in the liquidity of the market. The liquidity was coming back in the morning of the successive day. If not, it was virtually impossible to continue. But anyway, it was coming back because the central bank was borrowing again, only for that reason. So it was a virtual restitution. I can restitute to you $1 million if you give me immediately the $1 million back to me. It's only an account movement. The idea of the automatic settlement is wonderful if no delay, voluntary or involuntary delay. Voluntary to speculate upon time, involuntary if I have no absolutely money, and for reputation reason I don't want to announce that. And in this case, the automatic settlement system is absolutely unable to solve the problem. We have delays in payment, we have liquidity shortage, and if you have a shock, also a very small shock, in a day of the August of 2007 in Italy, in July of that year, it was the network of the European banks, the network of the European banks, which is running upon the internet system, was unable to work for a few hours, and in Italy we had a terrifying liquidity shock with huge risks. And the financial crisis can be exogenous or generated endogenously or amplified endogenously by the delays I was explaining before, with huge domino effects. So, in the simulation model, we have two different parts interacting exactly yesterday and today. In the first part of the morning, I was looking for a strange case of interaction between the two parts of the model. I discovered that it is not an error, happily, but it is a so rare event that apparently had the look of an error. Do you know, there is a joke about from Axtell and Epstein. It's not a joke, it's a sentence. If you have an accounting program producing a strange value, you are looking for an error. If you have a simulation model producing a strange error, you are trying for a discover. We found an emergence. Maybe it is an error. So my problem was that if the case arising from the model which is now running inside the Bank of Italy that produced a few days ago a very strange error was an error in the interaction of the two subsystems, or was an actual event, and it was a rare actual event. Because here you have a flow coming into the model from outside. Is the world which is generating the data. Now we are working only on data of the past, but our goal is to work on real time. So data as generated by the payment among the system of the Italian banks. So you have here a flow of data coming from outside, and the model, via the decision of the treasurer, is executing all the payments, and when necessary, the treasurers will interact with the stock market of the money, bidding or asking for money. To bid is to offer a price, to have money, to ask is to ask a price to borrow money. We simulate delay, and we look to the emergence of realistic, interesting rate dynamics into the electronic market for interchange deposit. Here we put a lot of statistics, because having a look to schemes of autocorrelation, we understand if in the short term some chain of events is arising into the reality, into the model, and then into the reality. This is the reason I put here a magnifying glass. In this case, agent-based simulation is a magnifying glass to understand reality. And I underline, to understand reality in real time, not now. But our idea is to have the capability of having the model effectively running by the end of the year, maybe after the summer. We are very, very close. Within the model, we have complicated microstructures. This is one of the wonderful sides of the simulation when you build a realistic model. You have to open any black box. You cannot have black boxes there. You have to go very, very close to the reality. I cannot explain now all the details, but this is quite simple to be understood. Do you know that one of the huge problems in our model is parallelism? What parallelism means? In real life, if I ask you to do something, you are doing something all together, someone a microsecond before than another person, but this is absolutely not important. In the computer, we have to simulate parallelism in an artificial way. But what if the reality can be? The reality can be both parallel or sequential in different time of the day. So in the bank system, we have the beginning of the day where mainly the events have parallels. Starting the day, treasurer are sending back money to the creditors, are sending back money to Bank of Italy, are paying something of mandatory like taxes for their client, and so on. Then we have a phase of restitution of the payments, but then the world will be mixed with no more parallel diffusion of the events, but immediate and so sequential diffusion of the events. In the first version of the model, we completely forgot to have to pay attention to this kind of problem, and the realism of the model was suffering a lot. Now this has been a very good step ahead, and it is not easy to explain this kind of problem. I am trying to use a quasi-UML, do you know, Unified Modeling Language presentation, but this is not strictly the protocol of the Unified Modeling language. A second important problems in details, the devil is in details, you know, is if we look for the decision in asking and bidding. Because when we ask or we bid, we have to imagine a good price to be put into the logs of the system. Just 2 words to explain how a computerized book of a market, of a market for stocks or a market for money is exactly the same, works. You have 2 logs, and when the central book of the system receives an order, immediately looks if there is a counterpart. I am asking for money, so I place there that I will pay 2.5% of interest rate to have money. No one is bidding, I have no counterpart. My ask is put in a log. Then also Nigel is asking for money, and it is offering not 2.5 but 2.51, so 1 cent more. And the log is putting in first place the offer from Nigel, in second place mine. Finally, someone of you bidding finally, and maybe the match is possible, but if you are bidding less than our price, no match will be possible, and also your bid will be placed in the log. What about if you look to the last executed, so the last match in the past, or to the current new price put in the logs? Apparently it's the same, but the effects, I repeat, if I can imagine my price looking at the last executed operation, 3 minutes ago as an example, or to the last bid put by Nigel. And this is a lot different. You are concatenating the sequence of the events, or you are keeping the time frozen because you are losing to the previous situation. And a part of the treasurers is looking in this way at the mark, and the part is looking in this way. So you have to mix, you have to imagine different probability of participating in one way or in the other to the market, and so on. This is I don't know, a continuous discover. And again, talking about the making of a model, of a huge model, it is impossible to start having in mind this kind of details. Also our group, myself and the 4 colleagues from the Bank of Italy, we were not able in the beginning to define in a detailed way all the way to be followed in building the model. It is a continuous discovery, also discussing with, first of all, the treasurers. The treasurer does not explain anything of their work because it is a professional secret also. But discussing, it is possible to have a suggestion, to have impression, to have denies, and so on. A living model, so. Now some technical detail, because this is the creative part of building a huge model, but then you have to write code. And writing code is a heavy task always. I am using presently a creation of mine, because being one of the pioneers of the agent-based simulation, I started from Swarm. The alpha release of Swarm is 1994. The first beta has been 1995. The alpha version was terrible, also terrifying. It was deleting a workstation, as an example, if you are making something wrong, but it was an alpha version, so it was always possible. And from the first beta, written in Objective-C. Objective-C is a wonderful language, is C plus Smalltalk. Nothing. It's impossible to write, no problem. C plus Smalltalk. And Objective-C is now very used because Mac is using Objective-C to write the operation system. but in the middle of the 90s was very rarely used. I remember a discussion in the University of Trento. A colleague of mine told me, "You are crazy to use this language. No one knows it, about 100 people in the world, and 2 are here." So, and then the people from Swarm wrote an interface in Java, linking the libraries in Objective-C with the possibility of using Swarm in Java. And Java, well, in the 90s, was very diffused, and it is diffused also a lot now. But for a student, it's always quite complicated. A lot better to use a recent language like Python. Python is not the snake, is a joke with Monty Python BBC movies. Maybe do you know them? They stopped producing movies from about 20 years ago, but they are wonderful. And Guido van Rossum, who is a mathematician, is an aficionado of Monty Python, so Python is the name of the language coming from there. And also parts of the language have names coming from the character of Monty Python. Little bit crazy. But if you are a mathematician, you have to be crazy. I am partially crazy. So SLAP, with the P more than SLAP, is Swarm-like agent protocol in Python. Why to use the old Swarm protocol? Because the Swarm protocol, and you can have a look here to the seminal paper from Minor, Burkhardt, Langton, and Ashkenazi. The most interesting guy is Langton, that is continuously disappearing and coming back in the scientific arena. You have the foundation of of Swarm, where the main concept is that one. You have to think about those years, not today. Today, with NetLogo, we are building a collection of data. We are asking to the collection to do something. It is in our mind, but the origin is here, in the roots from Swarm. And the protocol of Swarm is hidden in repaste, escape, NetLogo, SterLogo, what you want, and is the constitutional part of my SLAP. So the container of our model, of our Bank of Italy model, and of a lot of all around our models, because the protocol is inspiring also other tools, the Swarm protocol, is this one. We create agents, but we put agents into collections. We create actions, and actions contain methods to be executed by the collections. When you build a NetLogo model, you create, I don't know, 100 turtles, and you put them in a collection. But if you create 1 or 1 million, 1 million maybe is too heavy for our computers, but I don't know, 10,000 is exactly the same. The scheme of the model is exactly the same. And this is one of the fundamental ideas of Swarm. You have to think that in the middle of the 90s, to have the capability of ordering to a collection to do something, you have to create a new part of the languages. So huge macros both in Objective-C and in Java. Now, with modern languages like Python, this is directly possible without any trick. So this is a huge advantage. Then you run the model. You have your bugs going around, doing something in a grid with a clock ordering things to be done. And the idea to have events as objects is from Langton. But the model is enclosed within a larger world, the world of the observer. We are the observer. The name observer is kept in NetLogo, do you know? And as observer, we have the model is a part of our world. We have another clock running the events of the observation. The observation can be also asynchronous if compared with the clock of the schedule of the model. We have reports, we have graphical reports, and so on. And we have two layers in our world. A third layer, a third tool, is the use of probes to go directly into the agent and to have a look to their variables and also to change on the fly some variables to discover errors. And you know, in NetLog it's a very common use to open a probe to an agent, and the idea is always coming from there. This is the container and the content. Or here I am advertising the paper of Nigel and myself you are recalling in the introduction is this one, how to build and use agent-based model in social science. And with a great surprise for me has been reported in the collection of paper prepared by Professor Guildford a few months ago. And I am the winner of a copy of the 4 volumes. It's the first time in my life I was winning something, 4 wonderful volumes. And the movie demonstrated that there's been a random choice, so no trick there. And the scheme environment agents rule has been introduced in this paper. Is not an original idea, but in this paper is the first time has been formalized, and you can have the scheme also from this web page. Sure, you can read the paper or have a look to this page, only for the ERA scheme. What the ERA scheme is offering to us? This ordered environment. You have here your world. Maybe this is an hospital, this is a stock market, this is a payment system, what do you want? Then you have several families. In NetLogo language, you have breeds containing 1, 2, what you want as number of agents. But the scheme is simplifying the world like a Lego game with this idea of bricks. This family of agents use this block as master of their rules. So it's like their brain. They have the same rules, so they have a unique rule master. This other agent have another rule master, and so on. We can easily modify the model simply substituting this brick. And if the interfaces are written correctly, all the machinery has to continue to work. But rules are not static. So you have to evolve rules in many cases, mainly via learning capabilities. And so we can have one or more generator of rules. Here the name is rule maker A, rule maker B. Rule maker A will modify those rule master, and the rule maker B will modify only this rule master. What in the rule maker and in the rule master? The first thing is fixed rules. This is very easy. In a lot of models, we have mainly fixed rule. But rule can evolve. And one very interesting and powerful way to evolve rule is that of the reinforcement learning, which is mimicking real life. I have a lot of grandchildren, and my grandchildren are exploring the world using reinforcement learning. They are doing something to follow a goal. If their action fails, they will not repeat this kind of action. If it is successful, it will repeat it. How to catch the huge quantity of data we are obtaining from reinforcement learning? One very easy way to catch this huge quantity of data is to build neural networks. In this case, neural networks are not magic, are simply function summarizing data from the reality. And what a neural network is very able to do is mapping an input vector to an output vector. And in this case, the input vector is information, the output vector is one or more actions. You will see I now have a very crazy idea, but it will be in the conclusion. Or you can develop something more complicated, like via genetic algorithm, new agents or new minds for agents. Or better, using genetic algorithm, you can develop new rules. So this is from Professor Holland, classifier system idea. Very complicated, but what a classifier system is. In 2 words, is a system evolving rules. Rules are all homogeneous, mapping an input to an output via 2 vectors, but chaining different rules, you can create any complicated level of decision. The problem is that of paying successes and making costly unsuccessful decisions, but it is only a problem of writing code. Finally, and this is a very interesting idea, you can put an avatar here. After the movie Avatar, anyone knows what avatar means, but avatar is a religious term from Hindu mythology, is the incarnation of a god, but in computer language, avatar is a piece of code representing myself somewhere in a model or in a game on the internet. In Second Life, I have an avatar. My name is Pietro Terna. My avatar is named Pietro Tank, which was the closest name and family name to mine. And the avatar is simply acting into simulation, substituting a rule master. Imagine that I won't put myself in the payment system as a treasurer. What I have to do? I have there a treasurer without a rule master. The treasurer sends back via a web page a lot of information to myself and waits until I will tell it what to do into the simulation. In this case, you have to run the model with a speediness compatible with our mind and our capability of reacting, but to slower a model is always simple. It's difficult to have a fast-running model. In the Bank of Italy case, we have here as environment the real-time gross settlement system and the market for money, and all the agents interacting with this kind of world, with their rules and evolving their rules. Okay? All the machinery is written in Python, following the Swarm protocol and using SLAP. I will advertise again a few minutes in the conclusion. Scientific advertising, because Python is completely free for the users. Now, a discussion. And if you want to help me in this kind of discussion, I will appreciate a lot. Pay attention, this discussion is very hard, and between myself and my colleagues from the Bank of Italy. They are putting into the rules more and more equations. And I'm trying in the opposite direction to avoid equation, but to put or fixed or evolving simple rules. Because treasurers are not deciding daily, having a look to an equation. They use their experience, and what the experience is the consequence of reinforcement learning, creating easy to be executed routines. In real life, we follow routines. But the fighting situation is to find an equilibrium between the simple, quotation marks, apparently simple. You can put any number of equations. From a mathematical point of view, this is very simple. But then you have a strange way of behaving arising in the model, and it's very difficult to control for the reason of this kind of behavior. Or you can put complicated definition of micro details. You have seen the micro details before, how they are complicated. But in this case, in my opinion, sure, you can control better the way agents behave. So, searching for the equilibrium between these two ways of building models is very, very important. A lot of friends of mine, I am considered being an old guy in the university, a consultant for everyone in the academia, a lot of colleagues of mine are writing equations. They are putting them into some form of interaction via mainly tools like MATLAB. Do you know MATLAB? MATLAB is Fortran, it's the same thing. It's not an intelligent tool, it's a tool for doing calculations. They put them in MATLAB and they tell me, oh, here you have an agent-based model of mine. Nope, I have a lot of equations interacting. This is not an agent-based model. You are not putting intelligence into the agents, and you are not looking to micro details to explain how, in the different situations, agents behave. You have not heterogeneity in your model, and so on. So, standard approach. You have equation, you are putting rationality into the agents, you are looking for equilibria via equation, aggregated equation, and as an example, clearing the market. You have bid and ask for money, you are clearing the market for money with calculating an equilibrium between asking and bidding functions. But this is not how the world works. In a day, we have a price for the money in the middle of the morning, another price at the end of the morning, and so on. We do not have a unique price, like in stock market, and like for buying tomatoes in the market. It's the same thing. The price is not unique, it's continuously evolving with a lot of errors within the process. And the consequence of this standard way of building models, I am quoting Trichet in a few minutes, is the incapability of our model in helping to making policies. And the demonstration is the last, unfortunately, is the last crisis. We can move toward a more close way of building agent-based model. And the first step is that a lot of friends of mine are doing, putting the equation into individual agents with some degree of heterogeneity, okay? But they are going closer to realism and social